for 2018-2019. How many of you are here first time? Thank you. Welcome. Special welcome to you. Those who are here first time, the Young Scientist Roundtable has been in operation for more than 26 years. It is being run by a group of volunteers who get together several times a year, and with an active support of Wayzata Public Schools, we present this program to several school districts in and around Twin Cities. The objective is only one, promoting science for K through 12. So let me ask the next question. How many students are here from elementary grade through grade 5? Raise your hands. Thank you. How many students are here from the middle school, 6, 7, 8? And how many students are here from high school? Quite a few. Okay, good. Thank you. So during the course of a year, we try to arrange speakers from different fields of science. Today we have a speaker from an engineering field. Dr. Joseph Labuz is head of the Department of Civil, Environmental, and Geo-Engineering at the University of Minnesota. He is the Miles Kirsten Land Grant Chair in Civil Engineering. He is an Associate Fellow of the University of Minnesota Supercomputing Institute. He holds a BS with honors in Civil Engineering from the Illinois State University. He received MS in Geotechnical Engineering and Ph.D. in Geomechanics from Northwestern University. He has received numerous honors for teaching and research, to cite a couple. He received Outstanding Achievement Award from the Minnesota Geotechnical Society and the Best Instructor Award in Civil Engineering from the Institute of Technology Student Board. His research activities have focused on investigating the mechanical behavior of microcracked solids. His research expertise is in experimental rock mechanics. For his inventive research, he has been awarded 2 patents. This evening, he has got a very interesting talk. His discussion is focused on listening to rocks, seismology at the micro scale. Let's welcome Dr. Labuz.
Thank you, Vinod, and thank you for coming, spending your evening here with me, talking about rock. So I'd like to start out, first of all, talking a little bit about the University of Minnesota. The university, I like to say, is older than the state of Minnesota. Of course, we have 5 campuses, and the Twin Cities campus is both in St. Paul and Minneapolis, and my college is on the Minneapolis campus. I'm in the College of Science and Engineering, one of 12 departments. We're somewhat unique in the United States in that we're a college of both science, physical sciences, mathematics, and engineering, which has several advantages. I'm in the Department of Civil, Environmental, and Geoengineering, and we have a very unique building because you see very little above ground. Most of it is below ground, so 95% of our building is underground. We have some outstanding faculty and students, and getting back to our building, it was the 1983 American Society of Civil Engineers. It won the ASCE Outstanding Achievement Award for use of underground space. We have outstanding laboratories, and I'll be talking about some results from the laboratory where I work, and that's the Rock Mechanics Lab. Finally, about the department, if you'd like to find out more about what has gone on over the years, some of our contributions, we've recently put together what we refer to as a coffee table book. So the coffee table book is accessible from our home page, and that's just the first CEGEUMN will get you there. Okay, with that, I'd like to begin our topic. First, of course, I'm going to be presenting results that aren't just from my work, but I've had the pleasure and the opportunity to work with some outstanding students. So some of them are identified here, as well as some outstanding colleagues, both at the University of Minnesota and also in Italy, in the Politecnico di Milano. Okay, with that, one of the major problems in engineering, in several branches of engineering, is to be able to identify what is often referred to as the mechanical response associated with failure. So certainly you're aware of some of you are aware of the tragic events that took place just over 11 years ago. That was the collapse of the 35W bridge. So indeed, that was a tragic failure that should never have happened. And engineers spend a great deal of time evaluating materials, evaluating designs to make sure failure doesn't take place. But there are examples, there are also cases where we do want to develop failure, and especially within the area of geoengineering, in creating a tunnel within rock, in excavating rock, we want to bring about failure. So I have two examples here. One is of our building. So this is the mine space within the civil engineering building at the University of Minnesota, where you see basically the cavern that's created to form this mine space. So this vertical hole is referred to as a shaft, and then the rock was excavated, and you see a portion of the rock that remains. In fact, one side is a portion of the pillar, and of course this is the end of the excavation. And the other example I have is one of a drilling bit. So I want to break the rock, I want to excavate the rock, so indeed I need to fail it. And I want to know under what conditions might I efficiently, with the least amount of energy, excavate this rock. Again, a few other examples where these are cases where failure was not welcomed. It should not have happened. But again, there are cases where we do want to develop failure, and we're going to be looking at those cases and identifying characteristics about how the material is failing that may help us certainly understand how it's failing and then improve methods for causing it to fail. I'm going to start out, though, well, hopefully more than reviewing, but telling you a little bit about rock from the perspective of a civil engineer and not from the perspective of a geologist, of an earth scientist. So to me, the particular origin of the rock is not that critical. More critical to me are its mechanical properties. And I'll review with you, or I'll explain to you some of these mechanical properties. So, in a very simple way, I could think about rock as a collection of grains that are glued together. And certainly because I have a collection of grains, there may be space between these grains. And that space could be I could simplify it of two forms: pores, so spherical-like cavities, or very thin, narrow cavities, more crack-like. And these features have a very important effect on how this material behaves. So I have an example here of a piece of material, piece of rock, that I instrument in a special way. And I instrument it in such a way that I could determine the volume change. So what I want to do to this piece of rock is subject it to pressure. So I'm going to take a fluid and place this rock in a fluid where I could increase pressure of the fluid. I'll isolate the rock from the fluid by putting a membrane around it, so the fluid is not going to enter the rock. And I'm going to be able to measure the volume change that takes place. And what I have plotted here is the pressure, hydrostatic pressure, versus volume change, or volume change divided by the original volume that I started with. And that's referred to as strain, volumetric strain. And I have to explain, though, these pressures now that I'm applying to this rock are fairly high. So, you know, atmospheric pressure is about 0.1 MPa, megapascals, 100 kPa, kilopascals, or we say 1 atmosphere, right? I'm applying pressure much higher, hundreds of atmospheres. And I want to see how the material behaves. So I start with a substance that is just quartz that is a solid, has no pores. And the response is I would describe as nice. That is, it's linear. There's a linear relationship between pressure that I apply and volumetric changes taking place. But within rock, you see a behavior that is, I would describe it as nonlinear. And what's taking place here? You have a pointer? No? Okay. What's taking place here is some of the cracks are closing. So this nonlinear behavior is due to cracks closing. And what I'm seeing here in this linear part is the behavior of the collection of grains and the pores between the grains. And this behavior is very important in understanding how this rock is going to behave under certain types of loading conditions. So, for example, of course, rock in the ground is surrounded by other rock that pushes on it. So if I excavate a hole, I'm going to change how these forces are acting within the rock. And I need to know how the rock behaves to make sure that the tunnel, in this case, is safe. Okay, another example or another feature of any rock-like material. So oftentimes we use this term rock-like, and that is if I take a piece of rock or a piece of concrete or ice or ceramic and I apply a force to shorten the specimen. So we refer to that force as a compressive force, and I measure and I apply the largest force I can to that material. So there will be a limit to the amount of force that I can apply. And if I measure the force and I know the cross-sectional area, I could define a term that is called stress. So we can think of stress as an internal force per area. And there will be a maximum stress that I could apply to this material. Now, if I take this same material and instead of squeezing it, applying a compressive force, I pull on it. Rock-like materials are very strong in compression, very weak in tension. So this ratio of the UCS, which I'll use the symbol capital C sub 0, and the tensile strength, UTS, and I'll use the symbol T, that ratio is greater than 10. And I have an example here of one of the rocks that I showed previously, and those rocks, by the way, were sandstones. So this also is a sandstone where if I apply compression, I measure a strength of 20 MPa. If I apply tension, the strength is 1.5 MPa. So a drastic difference. In addition, another very important behavior that's shown here is this slope, when I apply compression, is higher than when I apply tension. And that's because of the presence of the cracks. So again, this mechanical response is important for an engineer to be able to excavate the rock in a safe manner or to be more efficient in how we excavate the rock. Okay, so some more mechanical response. Now we'll get a little more complicated loading. And this is loading where I apply pressure, but after I apply pressure, I want to squeeze it. And this now is getting closer to what happens in the earth. Because in the earth, of course, there is neighboring rock. And the deeper you go, the more stress or pressure there is surrounding that piece of rock. So as I go deeper, what this behavior is showing is as I change the pressure. So this blue curve and this red curve are two different experiments on the same rock, but under the condition where I start out with a different pressure. And the larger the pressure, the more force that rock could take. So as I go deeper, one way of thinking about that is the rock is getting stronger. And certainly the behavior of rock as we go deeper becomes very important because we want to, for example, extract minerals, resources in the earth. And drilling a hole and keeping that hole open is an important part of extracting those minerals. Okay, one other type of behavior before we get into listening to rock, and that is some rock can change behavior by applying just pressure. So I started out showing you an experiment where I applied pressure, I closed some cracks, but then the response was very nice. It was a linear response between pressure and volume change. There are some rocks, and some of these rocks are very important to us because they contain minerals, resources, hydrocarbons. This is an example of a chalk. Chalk is a material, is a rock that is quite porous. This is a porosity of 46%. So if the chalk was just uniform spheres, this would be the highest porosity that I can have for all these spheres to touch. So very porous rock, and indeed the phenomenon, or what happens in the earth, when we extract fluid from the rock, we're changing the pressure. And if the rock is deep enough and if we extract enough fluid, oil, the pressure change can be high enough that we could, well, break the rock. So what I'm showing here is, again, a response of pressure versus volume change. Nice behavior that it's linear, but as pressure increases, the behavior changes. And in fact, what's happening here is I'm failing the rock. The rock is, the pores in the rock are collapsing. And this is a very important type of behavior because if the deposit in which we're extracting this oil is several tens of meters thick, the amount of settlement or subsidence that can take place can be quite large and certainly detrimental to a structure or something else that is above this rock. Okay, so that's kind of an overview on the mechanical response of rock. Now we want to listen to rock. And this example is one where indeed you're going to be able to hear the rock. This is a tunnel, 20-kilometer long tunnel in Peru. It's excavated by a tunnel boring machine, a TBM. So a TBM is a very large drill that makes this 18-foot diameter, this 5.3 meter diameter hole in the earth. About 12.5 kilometers was through the Andes, where over a mile of rock was above it. And something was happening, and that something is given the name rock burst. So there were over 10,000 rock bursts, and you're going to hear rock bursts. And basically the rock was failing. So if you want to view this, this video, it is on YouTube. So I'll pull it up. And let's play it. So we're underground in an 18-foot diameter tunnel. Sorry about that. So let's try again. Thank you. hopefully the audio will come. So we're underground. This is some equipment that is providing some support to the tunnel. You see pieces of steel. Those are steel sets that help support the tunnel. And you should see rock flying, and we should be hearing rock breaking. The volume was up. So it was working before, you guys came. So that is rock breaking, and that phenomenon is called rock bursting. So in this case, the miners are listening to rock. So we'll try again. Although, I mean, it's nothing much to listen to other than... So this rock breaking has been used to monitor the safety of an excavation, and in fact it's a very common technique for deep underground mines to ensure the safety of miners. This type of behavior can be quite violent, and there have been deaths that have resulted because of this behavior. So if you're a mile underground and you hear it happening, so of course those are miners, but that is rock breaking. And of course you see the dust and the pieces of rock that are flying. Okay, that was the big one, so I'll stop it. Where did it go? Okay, so that's certainly listening to rock where we can hear it with our ears, but there are things that are happening before we hear it with our ears, and we can use particular types of instruments, and these instruments are sensors, and the fractures that we're going to be listening to are this phenomenon is referred to as acoustic emission, AE. So there are many applications where we want to fracture rock, and this comes about by a number of different ways. It could be by temperature change. It could be by this stress that we're applying to the material. Basically what happens is the material has defects, has small cracks and pores, and depending upon the change in stress, this crack can grow. And when the crack grows, it releases energy. Part of that energy is in the form of an elastic wave. It could be a sound wave that we hear, but if the crack is very small, so what we hear will be dependent on the size. So larger size cracks we can possibly hear. Smaller size cracks we can't hear, but we can record. And these small cracks, as I said, this transient wave is referred to as acoustic emission, and this is one of those signals that we can record by cracks forming within the material. So we want to use this information, this signal, to tell us something about how the material, how the rock is behaving. Are there cracks forming? Where are the cracks forming? And how strong are those cracks? And certainly these are questions that a seismologist asks and answers as it relates to earthquakes, right? We want to know where the earthquake took place, the location. We want to know the strength of the earthquake, the Richter magnitude. So you know that bad earthquakes, strong earthquakes could have a Richter magnitude of 6 or larger. For us, our Richter magnitudes are -4, -5. And the Richter scale changes by factors of 10. So we're talking about very, very small amounts of energy that are released. But we can use the same techniques that are used to study earthquakes, to study these small cracks. Okay, so that's what I'm going to be presenting now, results on finding these small cracks. I want to locate them. I want to see what's happening to the material because I'm doing something to it in terms of causing this fracture. And then I want to find out how strong these cracks are. That is, how much energy was released by these cracks. Now, of course, as I said, this problem has a very important application. And in fact, this AE phenomenon was observed in the United States in the 40s in evaluating mining activity. So some of you may remember that we did in the Twin Cities have a Bureau of Mines. It was a research center right off Hiawatha near the airport. Obart and Duvall operated out of the Bureau of Mines in Denver. So they wrote 2 famous reports using this so-called microseismic technique to evaluate safety of mines. And this then really took off all over the world as a technique that is quite powerful in evaluating when the rock is breaking. Other areas of application have to do with materials. So there's a famous study that took place in Germany by Kaiser to use AE to evaluate how metals behave. And of course, within the area of seismology, that is the study of earthquakes, the theory, the analysis is quite rich in locating the earthquake and in telling us the strength of the earthquake. So we'll be applying those techniques to little cracks that appear well in laboratory experiments. To put in a plug for civil engineering, there are a number of applications in civil engineering where acoustic emission is used for bridges, bridge decks, looking at behavior of materials, and so forth. Okay, so let's move along. This is going to be results from laboratory studies, so it's going to be small-scale experiments. So I'm talking about pieces of rock that are on the order of tens of centimeters, and we'll be using instruments that have the ability to record these time histories. And one such instrument is shown here. It's really quite simple. It is a piece of a material that has a property of piezoelectricity. So a natural material such as quartz is piezoelectric. And what that means is if I stress it, so if I produce some type of loading on this material, but this loading has to take place rapidly, a charge will develop. And if I measure that charge, I could say something about what was happening where I had this sensor, this piezoceramic material. And that's what we're going to use to evaluate, to capture these signals from the AE, from the acoustic emission. Another very important characteristic of the data acquisition system, that is, I have to record these signals. These signals have a high frequency, so I need a fast data acquisition system. So I'm going to use a digital oscilloscope. So an oscilloscope to be able to record these high frequency waves, and digital such that I could easily manipulate, easily perform some signal processing on this information. For us, a key bit of information is location. Location, location, location. So I'll be able to find where that little crack took place. And there are a number of ways of doing this. Well, first I should mention that in terms of how well could I locate that event, within a few % of travel distance. So if my travel distance is on the order of tens of centimeters, let's say 10 centimeters, then I could locate it within a few millimeters. So my locations, I believe, are quite good. The important bit of information, so what I'm showing here are 4 time histories, 4 signals from the same crack, from the same event, recorded by 4 different sensors that are located at different positions on the specimen. And from this information, specifically the arrival of the wave at each sensor and the position of the sensor, that is, I know where I glued that transducer, that sensor, I can determine the location. And one way of showing this is, in fact, a graphical method. And that is what's shown here. The red are the sensors. This equation is a parametric equation for a hyperbola. So I have enough information here. R has to do with the travel distance from the event, which of course I don't know, to the sensor. I do know that the wave speed, how quickly this wave could travel in the material, that's represented by this C subscript P. And I could find delta T 12 as the difference in travel time in terms of the arrival of the wave at transducer 1 and transducer 2. Then I can construct one hyperbola or set of hyperbola. I do that for the other set and for the third set, and I construct 3 hyperbola where they intersect as the location. Okay, I can also do this numerically, which I would want to do because I have hundreds, maybe even thousands of events. So that's the way we proceed, and what I'm showing here now are results. These are results of each one of these little stars is a location of a little crack. And the type of loading that's being produced here is one where this is part of a beam that's being supported on the bottom at 2 locations. And I'm applying a load at the top. And for this type of loading condition, what happens is that I have stress, this force at the bottom that pulls the material apart. So it's in tension. That's where the crack is going to form, at that bottom fiber. So in the early part of loading, when the force is not very large, the locations are more or less random. But as the loading increases, and that's what's shown here, the loading's increasing, the events cluster. And what you should see is a clustering of the AE where the crack is forming. So this is a very good indicator of where the crack will be that I'll eventually be able to see. So the crack is not yet formed, but these AE are telling me that that's where it's going to be. And I could use different loading. This is an indentation specimen. This is an analog to cutting rock, because basically the way rock is cut is we take a steel tool and we push it into the rock. We indent it. So this is showing the formation of the crack for 2 different types of materials. Another type of loading condition is one where I could create tension that is in the horizontal direction, and you see these, again, locations that are forming the crack. Again, a different type of loading. This is with a beam, a different material, different size, and again, the clustering of events tells us where this crack is going to take place. Okay, so I hope I convinced you that this AE technique is a very powerful way of evaluating fracture. But it's good to have redundancy in our measurements. How good is this method in finding the crack? Well, I could use another technique that's called DIC, digital image correlation. And that's a technique where I basically want to track a particle. And the particle is really going to be a group of particles that's shown by this box. So I'm going to identify a particle by a number of particles within this box. Something's going to happen to my material, to my specimen. I'm going to stress it. So that box is going to move, and I'm going to find out where that box is after it moved. And the way I'm going to do this is by using digital images. I'm going to take a picture. So I show here, well, it's shown here as a circle, but that's a particle that I have identified in one picture, in one image. I'm going to find it in the other image, and that's going to allow me to determine the displacement. And that's important because you'll see how I can identify a crack from this displacement. So now let's look at some results. This is a result of this imaging technique where I'm plotting contours of displacement. So the different colors are associated with displacement in the x direction. So what this means is this dark blue, the particles at this position are moving to the left. The minus sign means to the left at a value of -5, at a value of 5, and it happens to be 5 microns. So very small displacements. And on the other side, more or less the same value, more or less the same value of 5, but to the right. And certainly what that means is that a crack is forming, because a crack is a feature where if you look on one side, it moves that way, and on the other side, moves the opposite way. That's a definition of a crack. So I'm identifying a crack which has a very small opening, microns in size, and I can compare that to what I see with my AE, with these locations. And indeed, if you look at the locations, I would argue that it's picking up where that crack is forming. And I could apply a slightly different loading where the crack forms at some angle, and you see the AE is picking up those locations very well. Okay, so I have this very nice technique that could identify fracture. Is there some way that I could quantify how grouped, how clustered these little cracks are? So certainly it's nice to look at it and say, wow, you know, that's where the crack is. But could I have some quantitative way? I want a number. I'm an engineer. I want a number that tells me that indeed I have a crack. And there is this technique using a fractal dimension. So in this case, I'm going to use a fractal dimension, a fractal number, to identify how scattered or how clustered these locations are. So we can think about this fractal dimension that if the events are totally at random, the fractal dimension will be 3. That is, they could be anywhere in 3D space. If the fractal dimension is 2, then they must be on a plane. And again, that is one way of thinking about a fracture. So a fractal dimension of 2 tells me that I have a fracture. And because, of course, the fracture may be tortuous and I can't locate the events without error, there's could be some scatter, certainly because the crack is tortuous. So this is an example of a fractal dimension in terms of these locations where the number is slightly above 2. But I would argue that this indeed is associated with a fracture. Okay, so now I want to perform an experiment and use this analysis to tell me when the crack takes place. So I'm running short on time, so I'm going to jump through this experiment. So I'm going to load the rock in a special way. And this is showing the rock. And these little brass buttons are where I put the AE sensors. So I'm going to put this rock in a chamber where I can apply pressure. and I can apply axial stress. And I want to monitor how this crack is forming. So when I started, there was no crack there, and then when I did this loading, I got a crack. So let's look at the AE locations. The other thing I did here was to put a hole in it to get the crack to start by the hole, so I know where to look, right? And you see a number of AE around the hole, which is what you would expect. And as I continue to load, something like a fracture seems to be forming. And it seems that the fracture is growing, right? So is there a quantitative way of evaluating this? And indeed there is, and that is this fractal dimension, that when it gets to be 2.5, and that is right where the load is maximum, the crack is formed. Okay. Now in 3 minutes, you're going to learn about how we can identify the magnitude of the earthquake. So location, location, location. How about the strength of the earthquake? How big was the earthquake, and what did the earthquake do? Did it slide? Did it open? Did it slide and open? And we can do that in the same way that we do that for earthquakes for these little cracks. So this little cartoon is a little crack, and this little crack is just opening, and it's opening in the vertical direction. And there's a way of representing this effect. That is, I could represent this little crack, this guy, by this combination of forces. Now, it has to be a special combination, but indeed there is a special combination of forces that could model, that could give me this crack that opens. And that's what I want to use to evaluate these little cracks. And that's what's used in seismology to tell us the strength of the earthquake. Okay, so I'm going to perform a test where, again, I have this beam that's loaded, so I support it at the bottom at 2 points, and I load it in the center, and I'm going to form a fracture. So let's continue. This is the rock, and this is how the rock looks later in terms of the fracture in the rock. And this is the fracture growing. These are the AE associated with that loading condition, such that a fracture forms. And I hope you agree that indeed in the beginning, so just a little crack, seems to be getting bigger. Certainly it's starting to grow. I continue opening the crack up, and it's getting longer, and the crack is growing. Now I want to apply this technique of telling me what type of cracks are forming. So what's the strength of the crack? You know, what's the Richter magnitude? And are the cracks sliding? Are the cracks opening? Okay, surprisingly, many, many little cracks aren't just opening, because of course the main crack is opening. But on the small scale, the cracks are sliding, because the large crack is tortuous. So the little cracks have to slide and open, and that's what this bar chart is showing. So this angle of this different angle measured is a measure of how much it's sliding and opening. And it's also shown here in terms of all these little dots representing each one of these little cracks. And it's also shown here with regard to the components of displacement, right? So I have a three-dimensional object. I could break up the displacement into the components in the X, Y, and Z direction. And in the X direction is the most happening with the crack, because that's where the crack is open. So indeed, that's where you would expect most of the displacement of these little cracks to be taking place, and that's what this is showing. So the component Bx times the area of the little cracks is the largest of the three components. There is a component associated with the vertical direction, and surprisingly, there is a component of the out-of-plane direction. Okay, so I'll skip that and go to the summary. AE is one of the best methods to identify fracture. So be it in a rock specimen, be it in the earth, in a bridge, in a mine, this technique is, in my opinion, the best way to identify where a crack is taking place. And of course, the way to do that is to locate it. And the location problem is not that difficult. Certainly this problem of trying to quantify the clustering is a little more challenging, as is the mechanism. So I'll stop here and entertain any questions. Thank you.
We'll take the questions. Chris is on that side. We'll take one question from this aisle and another from that. I've got one request here, Dr. Labuz. What you are planning to do in part 2? You want to?
Oh, yeah, thank you. So I did bring some pieces of rock, and I brought some sensors. So I'd be happy to go into more detail about the characteristics of some of the rock. So I kind of glanced that over. I did mention to you that some of the rock that we tested was a sandstone, so I have that sandstone. I also brought along the chalk so I could show you this. You could feel this porous, even more porous rock than sandstone. That is this chalk. And I also have some granite. I showed some results with granite. And I have some AE sensors, so we could look at the sensors and if you have.
So this format does not allow us to do the experiments. So in part 2, he's going to be showing some experiments. So young scientists, if you have time, if you are interested, it will start 10 minutes after 8, and it will go for half an hour. So we'll take the questions. Raise your hands.
What happens when you apply a quick, hard force to a rock? What happens when you apply a quick, hard force to a rock?
Okay. So I didn't talk about, and the term I would use is rate effect. So the loading that I was applying was very slow. I said I was applying force. So when I applied that force, it was done in, I could say, quasi-static manner. Static, meaning it doesn't change with time. Of course, it did change with time, but very slowly. If I applied a sudden load, there could be some effects that occur because of the different way the material may behave. So certainly a material that is rate sensitive is asphalt concrete, right? So asphalt concrete is a material that you often can see the result of is the force. If it's applied slowly, you often see a rutting taking place. Or it's applied rapidly, you don't have that problem. With regard to the mechanism, if I can call it that, of failure, that is fracture, the effective rate is not very strong. So similar things, or things that I've said, more or less apply no matter what the rate of loading is. I have some other difficulty in terms of being able to capture the information I need to tell you about locations, right? Because I need enough locations happening, and if I apply a force, a very large force over a very small time, I may not have enough time to acquire information. But the basic effect is the same.
One second.
Okay, and I was told I have to repeat the question. So what happens when you heat rock? That was the question? Yeah. Yeah, okay. So I did say, I used the term loading, and we could use different loading for rock. So one indeed could be weight, so I apply force, but it could also be change in temperature. Rock, and there are two different effects that can happen with temperature. One is an effect due to the geometry, and what I mean by geometry is if I'm drilling a hole in the rock, now I don't have just rock, but I have a hole and the rock. And I change temperature because of the geometry. I can develop, and I call them stresses. I can develop stress in the rock. So that's one effect. The other effect has nothing to do with geometry. It has to do with the material itself. And the way I think of rock is it's a collection of grains. And some of those grains are slightly different. And because they're slightly different at this very small scale, when I heat them, this grain may expand a little more than the neighbor. And that can produce these little cracks. So it does depend on the temperature. So the temperature I would need to go to is 300 C, so over 500 degrees Fahrenheit. But then I'll see something happening to the rock.
Oh, wow.
I'll monitor these little cracks.
Okay, next question, Chris.
What if you pull the rock and push it at the same time? Like your fingers are pulling it, but like this. I don't know how to explain it.
Could you, but in the beginning you said, did you say blow up the rock?
Yeah, pull and push. Pull and push it at the same time.
Okay. Well, if you allow me to push and pull in two different directions, I think I can answer it. That is, so what I mean by that, and possibly what you mean by that, I want to pull the rock in one direction, and I want to push on the rock in the other direction. And that's a very interesting loading condition. And in fact, the way I could describe that loading condition, believe it or not, is one where, and the term that I would use as an engineer, I'm going to shear the rock. I'm going to change its shape. So, if I go back to my first experiment, I applied pressure. When I apply pressure, the only thing that changes is the volume. I don't change the shape of the rock. So if I started with a cube, I apply pressure, I still have a cube, it's just a smaller cube. If I do what you want to do, and that is if I apply force that squeezes it, and I apply force 90 degrees from that, that pulls it, what I'm doing to the material is I'm changing the shape, I'm not changing the volume. So that's a very good loading condition that I would want to apply to see what's happening to the rock. And in fact, I did that, and I called that term Q. So there was a plot that I showed quickly where I have a different pressure than I want to apply, and then I apply a different Q. And one way of applying that Q is how you're suggesting. Although it's a little tricky to pull and push, at least I could think of this thought experiment that I could do that.
Okay. 1 second.
What would happen if you hit a rock with a laser continuously?
Okay. So the question was, what happens if I shoot a laser if I shine a laser on the rock? So certainly it depends on the intensity of the laser. So, right, we could take a laser pointer and I could shine it on the rock and nothing's going to happen. But I could also say that there is a technique. There are techniques to use a laser to measure displacement. So one of the things that was really important in some of the behavior I was showing is how the material is deforming. So I could use a laser to determine that displacement. I think you want to break the rock, right? So if you pump enough energy into the rock, you could break it with a laser. Now, it's not a very efficient way of doing it, but you can do it. So, in fact, there have been studies to use different heating sources to excavate rock. It's not a very efficient way of excavating rock, but you could do it.
Okay. And 1 second.
At what temperature does rock freeze?
Does rock freeze? Yeah, so rock is a solid. It'll stay a solid if I continue to lower the temperature. Certainly in effect, as was asked, in terms of heating the rock, but also cooling the rock. That is, change in temperature depending upon, for example, geometry. I said this effect of a tunnel, and I change the temperature. So if I lower it, I could generate stresses. And if I have a rock and I lower the temperature, it's possible that if I lower it far enough, that I can, because of locally, the grains are slightly different, that I can get some cracking. It's just that, of course, you may be thinking, and certainly, and I didn't say that, in the earth, well, I did say it because I want to extract oil, right? That's a fluid, that's a liquid, and certainly there are liquids in the rock. So if I freeze the liquid, certainly a liquid such as water expands when it freezes. You can fracture rock, and certainly you see that effect in many places in Minnesota.
So we'll take one more question.
How early can you detect an earthquake so people can go away from there?
So the question was, how early can you detect earthquakes? Yeah. Okay, I'll answer it a short way and a long way, or a longer way. I'm not a seismologist. I don't know anything about earthquakes. So that's the short answer. In terms of precursors, so there has been, and there is continuing to be a substantial amount of work looking at what I can call precursors, that is warning for an earthquake to happen. So possibly there could be small cracks happening before the big crack, something I didn't dwell on, but I showed in one of my slides. A big problem with these small cracks is they are high frequency, very small amplitude, and an effect of trying to measure this very small amplitude is that the energy is easily lost with distance. So if you don't have enough energy, we can't record those signals. So the technique that I was talking about in terms of this AE, it certainly depends on my ability to record those events. So this is not, it turns out that this is not a good way to detect earthquakes, but there could be other things that are happening that may give us the ability to do that. AE is not one of those.
So I think we are going to formally stop this particular session. As you know, the round 2, part 2 will be in a classroom, room number 201. It will start in 10 minutes. We do appreciate the time that Dr. Labuz has spent with us in teaching us about some aspects of seismology, listening to rocks. So in recognition of that, here is a small token of our appreciation.
Thank you.
Those who are here first time, there are cookies. You don't have to go to part 2. You can take a cookie and go home. Enjoy the evening. See you on October 8, Tornadoes. Thank you.